Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go through an exercise where we're going to check the monotonicity and boundedness of the given sequence. And in fact, there's a theorem that is covered in the lecture notes that if a sequence AN is bounded and monotone, without performing any analytic operations or using a graphing utility, we can deduce its convergency. So the given sequence is 2 plus 1/5 to the power of n. So we're going to check these two properties, boundedness and monotonicity, to deduce about the convergency. All right, let's hit the road.
First, we should start with the boundedness property. So let's just copy an back down here. An equals 2 plus 1/5 to the power of n. So that means I'm going to look for, and n obviously starts from 1, 2, okay. I'm going to look for upper and lower bounds. Okay, so 2 plus 1/5 to the power of n is always less than or equal to, in fact, less than 2 plus 1 to the power of n, because 1 is always greater than 1 over 5. So that essentially means that this term here is always less than or equal to 3. I can remove the equality sign because for any choice of the n here, starting from 1 going all the way to infinity, this will take the value of 3. But anyway, let's just keep it for the time being. And, well, without this term is always positive. So that means this 2 plus 1/5 to the power of n is always greater than or equal to 2, no matter what n is. Okay, so this essentially implies that an is bounded by two numbers, above and below, and these numbers are m and n in the description. So anyway, so an is bounded. Okay. All right, so to show the monotonic behavior, I'm going to look at an plus 1 minus an. So I'm going to check the sign of that. There we go. So an plus 1 is 2 plus 1/5. Sorry, 2 plus 1/5 to the power of n plus 1 minus 2 plus 1/5 to the power of n. Okay. So well, once you expand this out, okay, you can observe that 2's cancel. So now I have to look at this difference here. Okay. Well, I have a common factor over there because I can write this term as 1/5 to the n times 1/5 to the power of 1, which is 1/5. Okay, so 1/5 to the power of n is a common factor. So I pull it out. So it's 1/5 minus 1. That implies that this is equal to 1/5 to the power of n, negative 4 over 5. Okay, well, 1/5 to the power of n is always positive, but negative 4 over 5 is not. So this implies that no matter what n is, this is less than 0. So which essentially means that an is a non-increasing sequence, which makes it a monotonic sequence. Okay, so an is monotonic. Okay. All right, so an is bounded and monotonic. We can immediately deduce that an converges. Well, this theorem doesn't really tell us where or what number an converges to. So, well, to find a limit, we should obviously use the analytic tools. Well, in this regard, I have 1 over 5, which is a number less than 1. Any power of that is going to be less than itself, so that's going to take us all the way to 0. So this limit is going to converge to 2. So this is us using an analytic tool or Calc1 to verify that. But again, this theorem is very strong that if you have bounded and monotonic behavior of the sequence, that immediately converges, even though what number it converges to. All right, here is the table of sample values together with I also checked here an plus 1 over an, but you don't need to. But here, what is important to show is that an converges to 2, and this is sort of like the graphical proof of an converging to the number 2. All right, to sum up, we made use of the theorem about the bounded and monotonic sequences to deduce convergency. Again, this theorem doesn't provide us what the limit value is, but it just tells us that the sequence converges before we hit the road to calculate the limit, or before even we use the calculator or graphical aid to see what the behavior of the sequence is. All right, thanks for watching. I'll see you in another video. Bye.